as an example, let me go back to our old friend, a light rod with masses m on both sides, rotating about an axis, and let us fix this axis on some ball bearings here. Let this height be z, let this also be z, let this angle be theta, let the length of the rod be 2L, so that half of it is L, and I want to first calculate L, the angular momentum of the body. Remember, we calculated this last time, but I want to do it again, and this is rotating with angular speed, angular velocity omega, like this. L in principal axis rotation is going to be I1 omega 1 I plus I2 omega 2 j plus I3 omega 3 k, where these I, j, k refer to the principal axis of the body. Now, when the body is like this is a rigid body. Let me choose, this is the origin O, the x axis like this, y axis like this, and z axis is coming out. You can see these are the principal axes, and you will calculate this we did last time, I1 to be equal to 2 ml square, that is the moment of inertia about the x axis. I2 moment of inertia about the y axis is coming out to be 0, and I3 moment of inertia about the z axis will come out to be again 2 ml square. This is omega. So, omega has two components. Let me go to the next screen and show you. This is the body, this is omega, this is theta. I1 is equal to I3 is equal to 2 ml square, I2 is 0. Let me remind you, this is my x axis, y axis and z axis coming out, and as I said earlier, as the body rotates, these axes are fixed in the body, these axes will also move. So, the components really refer to the components at the time when this rod is in the plane of this screen. So, omega 1 you can see is going to be in this direction is equal to minus omega sine theta. Omega 2 is along the y axis is going to be at this point omega cosine of theta, and omega 3 is 0, and therefore, I get L is equal to I1 omega 1 gives me minus 2 ml square omega sine theta I, and rest of the other two are 0, because I2 is 0, it gives you 0 with this, and omega 3 is 0. So, the angular momentum is in this direction at this point. At this time, it is in this direction. As the body rotates, it will also come out of the plane. It will come out and go in again like this. Now, you see, as far as the mass, length, omega and sine theta, these are concerned, these are constants. So, the magnitude of angular momentum is going to be 2 ml square omega sine theta, and magnitude remains constant. So, the only change in omega occurs because it is rotating about an axis. L. So, change in L is going to be equal to omega cross L, and in general I can write this as omega 2 omega L3 minus omega 3 L2 I plus omega 3 L1 minus omega 1 L2 j plus omega 1 L2 minus omega 2 L1, okay, which in this case can be calculated to be, let me write it further, omega 2 omega 3 I 3 minus I 2 I plus omega 3 omega 1 I 1 minus I 2 j plus omega 1 omega 2 I 2 minus I 1. Okay. So, what we notice is that in general, purely because of the rotation, only because of the rotation, the quantity, because L is rotating about omega, this comes out to be omega 2 omega 3 I 3 minus I 2 along the principal axis x plus omega 3 omega 1 I 1 minus I 3 j plus omega 1 omega 2 I 2 minus I 1, okay, at any given instant. And in the case of this rod that we took, L is in this direction. So, at any time L is equal to minus 2 m L square omega sin theta I, omega is in this direction, omega cross L, you can see will come out to be coming out of the paper in direction 3. This was 1, this was 2 and 3 was coming out. So, it will be omega cross L, omega is this way, would come out in direction 3 and its magnitude is going to be magnitude of omega, magnitude of L times sine of this angle, this is theta, this is 90 minus theta, so sine of this angle is going to be cosine theta. You will see this will come out to be 2 m L square omega square sin theta cosine of theta in the direction k. Do we get the same answer from this? Of course. You can see omega 3 is 0. So, these two terms, the first term and the second term, are going to give me 0. The third term gives me omega 1 times omega 2 times I 2 minus I 1. I 2 is 0. So, it comes out to be I 1, which is 2 m L square with a minus sign, times omega 1. Omega 1 is minus omega cosine theta. So, that comes out to be omega cosine theta. Omega 2 is omega sine theta, another omega sine theta, and the answer. So, let me write it explicit. So, what we got in this rod, if it is rotating like this, this is L, and therefore, dl dt, which was omega cross L, came out to be 2 m L square omega square sin theta cosine theta k. On the other hand, if I calculate it using tau 1, which is dl1 dt, purely due to rotation, it is going to be omega 2 omega 3 I 3 minus I 2 comes out to be 0. Tau 2, which is dl2 dt, which is equal to omega 3 omega 1 I 1 minus I 3 will also come out to be 0. Tau 3, which is dl3 dt, is equal to omega 1 omega 2 I 2 minus I 1 will come out to be this. So, the torque is in this direction, and therefore, to keep it rotating, I have to keep applying a torque. As the body rotates, the torque direction also changes, and the torque is provided by these bearings here. If this height is z and it is symmetrically placed in z like this, then at this point, when the body is in the plane of the screen, the force here would be like this, and the force here applied by the bearing on the axis would be like this. So that there is a torque coming out of the paper, and the magnitude of the torque would be equal to 2Fz, where F is this force, and therefore I can also calculate how much is the force applied on the axis by these ball bearings. There is another way of looking at it. The same body, when it is in the plane, L we had seen is like this, and the body is rotating like this. L has two components. Let me call it L vertical, which is along omega, and L horizontal. This is going to be, if this angle is theta, L sine theta. This is going to be L cosine theta. As the body rotates, L is also rotating about it. Its magnitude is constant. You will see that this component along omega, this component remains unchanged. The only component that rotates is its horizontal component. Let us see how it rotates. This is the horizontal component LH, and it is rotating like this. So at any given time, the small change in the vector is going to be this way, and this is going to be equal to the rate of rotation omega, that is the component perpendicular to omega, so it is rotating with omega LH delta t, and therefore delta LH over delta t magnitude is going to be same as delta L over delta t magnitude, because it is only the horizontal component that is changing, and this is going to be omega times L horizontal, and this you can see is going to be, L was 2 m L square omega sine theta, this is 90 minus theta. So L horizontal is going to be sine of 90 minus theta of this, which is cosine of theta times omega, which comes out to be 2 m L square omega square sine theta cosine theta. And at this point, when the body is in the plane of the screen, horizontal component is going to be coming out of the screen, so that is the direction, 3 direction of dl dt, and this is going to be the torque required. Let us now take another example that we did last time, that of a rectangle moving about, rotating about its diagonal. The length of the rectangle is A and the width is B. Let us take our origin to be its center. Then it is easy to see by symmetry that these are the principal axes. Let us call this x axis, let us call this y axis, and z axis is coming out of the plane. If the mass of the rectangle is m, then I1, that is Ixx, is going to be m a square over 12. I2 is going to be m b square over 12, and I3 is going to be m over 12 a square plus b square. And therefore, the various angular momentum component are going to be L1 equal to, suppose this angle is theta, then L1 is going to be m a square over 12 omega cosine of theta, and you can see cosine of theta is going to be this divided by this. So this is going to be m a square divided by 12 omega cosine theta is going to be b divided by the square root of a square plus b square. Let me redraw the whole thing. This is the diagonal, This is how the plane is, axis 1, axis 2, this is theta, and this is rotating with omega, and therefore L1 comes out to be m a square divided by 12 omega cosine theta, which is b over square root of a square plus b square. Similarly, L2, this is axis 2, is going to be coming out to be m b square over 12 omega sine theta, which is a divided by this a over square root of a square plus b square, and L3 is 0. So, we have gotten L1, L2 and L3. You can see right away that L is not parallel to omega. How about the torque? To maintain this rotation, the torque would be equal to, we can use different arguments as we used earlier. Right now, let me just use L horizontal times omega. That is, if I calculate the horizontal component and multiply by omega, it is only the horizontal component of L that is rotating, and vertical component that along omega remains unchanged. So, L horizontal is going to be L1 times cosine of this angle, which is really, this is 90 minus theta, so sine theta. So, m a square over 12 b over square root of a square plus b square times sine of theta. Sine of theta is a divided by square root of a square plus b square. That is in this direction. The two component would have a horizontal component going in this direction. So, it will be minus m b square over 12 a over square root of a square plus b square times b over square root of a square plus b square times omega. Let me rewrite it. So, I have this body, this is L1, L2, L1 horizontal component is m a square over 12 omega sine theta cosine theta, which I can now write as ab over a square plus b square. L2 horizontal is m b square over 12 omega sine theta cosine theta, which I can write as ab over square root times divided by a square plus b square. There is no square root. This you see from the last screen. This all the product ab divided by a square plus b square, ab divided by a square plus b square times omega. And therefore, L horizontal is going to the right is equal to m a b over 12 a square plus b square a square minus b square. And therefore, the torque, which is L horizontal times omega, is going to be, or times omega, m a b over 12 a square plus b square a square minus b square times omega square. How about the direction? This is rotating like this, so this will be going into the plane, and that will be the direction of the torque. Suppose I fix bearings on the top and the bottom. To get torque going into the plane, I would need a force which is like this here and like this here. The net force is 0, but it gives a torque which is going into the plane of the screen. So, this is the torque required to keep the rectangle rotating with a constant speed omega. Let us now see how I get the same answer instead of using these horizontal components from the general expression which told me that tau 1 is equal to only by pure rotation omega 2 omega 3 I3 minus I2, tau 2 is omega 3 omega 1 I1 minus I3, and tau 3 is equal to omega 1 omega 2 I2 minus I1. Again recall, this is what we are talking about. This is the way the rectangle is. Since omega is this way, this is 1 at this point, this is 2, 3 is this way, omega 3 is 0, this comes out to be 0, this comes out to be 0. How about tau 3? It comes out to be omega 1, which is omega cosine of this angle. So, this will come out to be omega cosine of this angle is b over a square plus b square root times omega 2, which is omega sine theta, which is omega a over square root of a square plus b square, times I2 minus I1, which is m over 12 b square minus a square. So, this gives me the same answer, m a b over a square plus b square 12 omega square b square minus a square. This is, remember, third component. This is negative, means is going into this plane of the screen. So, this gives me the right direction as well as the right magnitude as we calculated earlier, which was this was a square minus b square, but it was going into the plane. Similarly here, since axis 3 is coming out of the plane, I get a negative tau 3. So, that means torque again is going into the plane. As a variation on this problem, let me ask you to do a problem where this plate is kept at, the rectangle is kept with its plane making an angle with the vertical, and it is being rotated like this. I want you to calculate, so that it is normal to the plane, is at an angle with the rotation axis. I want you to calculate how much torque would be required to keep it rotating. I leave it for you to solve, although I am going to solve a related problem, that of a disc tilted at an angle from the vertical and rotating like this, so that is perpendicular to the disc, makes an angle theta with the axis of rotation. I want to calculate how much torque would be required to keep it rotating at a constant omega. Again, you see, now I will take this middle point, center of the disc, as the origin, and see that this, one of the diameters is a principal axis, so is the other diameter, and third axis is going to be coming out of perpendicular. So, it will be in this direction itself. This is direction 3, and I want to calculate what its angular momentum is and what is the torque required to keep it moving. So, let us make this picture again. This is a disc rotating with this perpendicular at an angle theta with omega. This is axis 2, this is axis 1, and this is perpendicular is axis 3. You can see I1, we had calculated it earlier. The moment of inertia about one of the diameters is m, if the radius is r, square over 4. I2 is also going to be mr square over 4, and I3 is going to be mr square over 2. Omega has components at this point in direction 2 and direction 3. Omega 2 is equal to omega sine theta, omega 3 is omega cosine theta, if I want to calculate torque, tau 1 and omega 1 is obviously 0, omega 2, omega 3, I 3 minus I 2 gives me I 2 minus I 3 is mr square over 4 omega square sin theta cosine theta. Tau 2 is going to involve omega 1, omega 3, whatever, this gives you 0 because omega 1 is 0, and so is tau 3, which is also going to involve omega 1, and that is also coming out to be 0. So, in this case, the torque is going to be in the direction along 1. At this given situation, the direction 1 is going to be coming out of the plane of the paper. So, let me make it again. Let us look at this disc in the position when it is like this. 1 is coming out of the plane, 2 is like this, 3 is perpendicular to the disc, and it is rotating like this. This angle is theta, and we see in this case that the torque is coming out to be tau 1, which is mr square over 4 omega square sin theta cosine theta, as we saw in the previous slide. Tau 2 and tau 3 are 0. So, torque direction is this, coming out of the plane of the paper. So, if I have bearings here holding this, the force is going to be this way and this way. Let us look at the same thing again from by taking the horizontal component of the angular momentum. The angular momentum is going to have no component in direction 1 because omega 1 is 0. L2 is going to be mr square over 4 times omega sin theta, and L3 is going to be mr square by 2 omega cosine of theta, and therefore, let me make it again, 2, and at this point 1 is coming out, 3 is like this, L1 we saw is 0, L2 is, this is omega, this is theta, L2 is mr square over 4 omega sin theta, L3 is mr square by 2 omega cosine of theta. So, L horizontal is going to be L3 horizontal minus L2 horizontal in this direction. You can see L3 is greater than L2, and this comes out to be mr square over 4 omega sin theta cosine of theta. Tau, that is a change in L, is going to be LH times omega, which is going to be mr square over 4 omega square sin theta cosine theta, which is the same answer that we obtained earlier. Tau 1 equals mr square over 4 omega square sin theta cosine theta in direction 1, and here also we see that since this horizontal component is pointing towards the left, it will be coming out of the paper of the screen as the disc rotates, and therefore again it is in direction 1. So, through these 3 examples, what I have shown you is, even if omega is constant, L magnitude could also be a constant, but dl over dt is not equal to 0 because L is not in the direction of omega. In all these cases where we had the components of omega along 1, 2 and 3 in such a manner that L magnitude was a constant, although there was a torque applied, but dl dt was not equal to 0, and therefore there was a torque required. We could calculate the torque either by using the general equation, which was tau 1, which is dul1 by dt, purely due to the effect of rotation, which was equal to omega 2 omega 3 I3 minus I2, tau 2, which was dl2 over dt, purely because of rotation, which was equal to omega 3 omega 1 I1 minus I3, and tau 3, which was dl3 by dt purely because of rotation, equals omega 1 omega 2 I2 minus I1, or by taking the horizontal component of L and multiplying by omega, seeing how it is sweeping around when the body is rotating.